Swayam Prabha. Digital India. Educated India.
In this particular class, we are going to discuss linear programming further examples. So far, we have already seen the linear programming, how the simplex method is used. And we have also seen various formulations and graphical solutions of problems. And mainly we have done maximization type of problems. We shall take up minimization problems a little later. And however, we have also seen various kinds of constraints and variable types. So also we have studied the importance of the shadow prices and the B inverse matrices. Here we are going to take a small break from the theory portion, and we shall see some more linear programming problems, how to solve them. We'll take up some formulation problems, some graphical problems, and also how some of these problems can be solved by the simplex algorithm. So here is a problem which we have already discussed the formulation part of it. But the modeling part of the problem we have not discussed. So how to formulate into an objective function and a set of constraints that we had discussed for this particular problem. Anyhow, let us go back and a quick revision of what we have already done. So an assembly requires two parts, one each. Part A requires 2 minutes in drilling machine and 20 minutes in milling machine. Part B requires 5 minutes in drilling machine and 15 minutes in milling machine. The times include the setting as well as loading, unloading times. If there are 1 drilling and 5 milling machines and all machines work for full 8 hours, how many of part A and part B should be produced each day so as to maximize the total number of assemblies? So here basically what is really happening is that there are two parts. Both the parts require drilling as well as milling operations. Different times are required, and we are ignoring setting, loading, unloading times. Here one thing is to be remembered that we have to maximize the total number of assemblies, not individual parts. And we know an assembly makes two parts, one each of part A and part B. So what we had done that supposing x1 is the number of parts produced, x2 is the number of part B produced. So these are the constraints because 8 hours of working, and there are one particular day has 480 minutes. So in terms of minutes, since only one drilling machine is there, so with that one drilling machine, the total number of minutes available on the drilling machine is 480. On the other hand, there are 5 milling machine available. So total minutes available on the milling machine is 2400. So the constraints, because the 2 minutes are required in the part A in the drilling machine and 20 minutes required in milling machine. Here it is 5 and 15 minutes. So we have 2x1 plus 5x2 less than equal to 480. 20x1 plus 15x2 less than equal to 2400. So these two constraints are pretty straightforward. But the question comes that what should be the objective function and how do we model the maximization of assemblies? So it's an important question before us that how do we maximize the number of assemblies? Now we know an assembly requires one part A and one part B. So we need to maximize the assemblies. Now maximizing production of part A is not the answer, because if you just make maximum number of A and not make many Bs, then what will happen? The number of assemblies will still be less because B is less. And on the other hand, if you make B more rather than A, again your number of assemblies will be dictated by A and not B. And if you make both part A and part B together, even then there could be imbalances. It may not be equal number of part A and part B. You see, technically equal number of part A and part B, suppose you make a constraint, but that would be too hard a constraint, because if you say that maximize part A plus part B and also take a constraint that is part A equal to part B, number of part A equal to number of part B, the problem is that that will be too hard a constraint, and we cannot take benefit. There might be a lot of idle hours in both the machines, or at least one of the machines. So that's not a very good idea to really maximize production of part A plus part B with a constraint that part A equal to part B, because then machine utilization will not be much. And in that sense, the number of assemblies will not be also made to the extent that is possible, because you have put a hard constraint which may not be necessary. So idea is that the number of assemblies produced should be less than the number of part A or part B produced, and in fact it is equal to x3 equal to minimum x1 and x2. But using mean function will keep the linearity, will not keep the linearity of the problem. So what has happened, if you it is should be less than equal to, not just less than equal to number of part A or part B. That means it is the lower of the two. That is, you can use the mean function, but moment you use the mean function in that sense, the linearity of the problem is not there anymore. But linear programming requires the objective function and all the constraints should be linear. So if the linearity is disturbed, then we have a nonlinear problem, and the benefit of the linear programming is not available. What is the benefit? That the basic feasible solutions are optimal solutions. That means if I have a solution space, we have to check only the corners. Feasible corner points, they are the basic feasible solutions. So that advantage will be gone. Then we have to see the entire solution space. So we have to, and also handling such, kind of functions are also not going to be easy. That will be difficult. So if that is so, then what should we do? So we need to maximize assemblies. So idea is to consider a new variable x3, which is number of assemblies produced. Suppose we just take an x3, which is the number of assemblies produced. So objective function is now very clear cut, maximize z equal to x3. But how to model x3? Because already we know x3 is the minimum of x1 and x2, right? So here you see this is an inventive way of putting things, that we can simply take x3 less than equal to x1 and x3 also less than equal to x2. It will ensure that x3 is minimum of x1 and x2 because we are maximizing x3. So what has happened in an innovative way, we have been able to model the system without using a function like the minimum function, which has a problem with the linearity of the problem. But here we are having both linear constraints, and we are able to then formulate the problem. So here is the complete formulation. X1 is the part A produced, X2 is the part B produced, X3 is the assemblies produced. So objective function maximize z equal to x3, subject to 2x1 plus 5x2 less than equal to 480, a drilling machine constraint, 20x1 plus 15x2 less than equal to 2400 milling machine constraint, and x3 less than equal to x1 assembly constraint, and also x3 less than equal to x2 another assembly constraint. And obviously the nonlinearity constraints we must add, that is all these x1, x2, x3 must be greater than equal to 0. Now we have already formulated the problem. Let us say now how to solve the problem. So in order to solve the problem, first we have to have the the augmented problem. So in order to have the augmented problem, first of all, we should not have any variable on the right hand side. So these x1 and x2 we must bring on the left hand side. That means we can rewrite them as minus x1 plus x3 less than equal to 0 and minus x2 plus x3 less than equal to 0. It is better to keep the less than equal to type of constraint, because in that case we do not have to add any artificial variable. Is it not? We can simply manage with some slack variables. So how many total slack variables will be required? There are 4 constraints. So we need 4 different slack variables. Is it not? So once again, that we cannot keep any variable on the right hand side. So we have to bring this x1 and this x2 to the right hand side. In that case, we shall have 4 constraints and we can add 4 slack variables, that is maybe x3, x4, x5, x6 to get the augmented problem. So here is the augmented problem. Instead of x3, x4, x5, x6, we have taken s1, s2, s3 and s4. So this is the original problem and this is the augmented problem. So you see the augmented problem is maximize z equal to only x3. So rest of the variables, they all are going to have profit coefficient equal to 0. So not only the slack variables are having 0 profit coefficient, but also the x1 and x2, the number of part A and part B, that also is having 0 profit coefficient. Now 2x1 plus 5x2 plus s1 equal to 480, 20x1 plus 15x2 plus s2 equal to 2400, minus x1 plus x3 plus s3 equal to 0, and minus x2 plus x3 plus s4 equal to 0. And all of these variables are greater than equal to 0. Those are our non-linearity, those are our non-negativity constraints. So now we have to to express it in the simplex fast table. So in the simplex fast table, how should it look? So we have these how many total number of variables? 1, 2, 3, 4, 5, 6, 7. There are 7 variables. How many variables will be in the basis? 4, because there are 4 equations. So S1, S2, S3, S4 will be equal to basis in the basis, and can you see that they are forming the unity matrix, and because of that the equations are in canonical form, and these are the values, that is 480, 2400, 0 and 0. So this is how therefore the entire table is put, that is S1, S2, S3, S4. They are in the basis 480, 2400, 0, 0. They are the values and these are the variables. And you see the unity matrix is formed by S1, S2, S3, S4. And these are the X1, X2 coefficients. So what are the basic variables? The S1, S2, S3, S4, they are the basic variables. So what are their Cj minus Zj? That is profit. Net profit to bring one unit into the basis. So since all these Cj, Ci are 0, so Zj, that is loss profit per unit, equal to 0 for all the variables. Now these are the Cj values. So Cj minus Zj for x1 is 0 minus 0 equal to 0. x2 0 minus 0, 0 is Cj, 0 is Zj. Zj is 5 into 0 plus 15 into 0 plus 0 into 0 plus minus 1 into 0. So 0, that is the Cj minus Zj. And x3, it is 0, 0, 1, 1. And Zj is still 0, but Cj is 1. So this is 1. So Cj minus Zj is positive for the variable x3. So x3 should come into the basis. Now, which variable should go out of the basis? You can see this, that these two S1 and S2 are not required to make X3. So therefore, they are not bottleneck resources. Which one could be a bottleneck resource? That S3 and S4. So we have a tie out there. Is it not? We have a tie. So either S3 or S4 can leave, and let us use S3 because of Bland's rule. We'll discuss that later. So, then we have X3 into the basis and S3 leaving the basis. So this is how we can continue the simplex and we can solve the problem. So we have not solved the problem. We are stopping here that how to really proceed with such kind of problems. First of all, how to formulate, and thereafter how to solve it by the simplex. Right. So let us now take another problem, that is the byproduct problem. So in this byproduct problem, we have already discussed earlier the formulation part of it. So in a chemical process, two products A and B are produced. Both products need two operations for the production. A requires 2 units of a certain raw material in operation 1 and 3 units in operation 2. And B similarly requires 3 units and 4 units in the 2 operations. And total raw material available is 16 units in operation 1 and 24 units in operation 2. Now, apart from this, a byproduct C is also available whenever product B is produced 2 times the volume of product B. However, only 5 units of byproduct is profitable. So what is happening? So, see, B is produced. Suppose B you are producing as 2 units, then number of byproduct C available will be 4 units, 2 times the volume. So no issues. But suppose we produced 3 units of B, then 6 units of C would be produced. What will then happen that out of these 6 units of C that is produced, only 5 units of byproduct is profitable. The remaining 1 unit, which is the not profitable part of part C, that has to be, destroyed at a cost of ₹2 per unit. So that is, if you produce more B, you will get more C, but only 5 units of this C would be profitable. Remaining units, not only they are not profitable, but they are to be destroyed at a cost. So cost of ₹2 per unit. So these are the issues, and if profit per unit for the products are ₹4, 10 and 3, find how much of the products are to be produced in order to maximize profit. C is the profit part, and there is also the non-profit part if it is beyond 5. So this is how, so these are the unknowns or the decision variables. X1 is the product A produced, X2 is the product B produced, and X3 is the byproduct C produced. So these are straightforward from the raw material consideration, that is 2x1 plus 3x2 less than equal to 16, the raw material requirement in the operation 1 for the product A and product B, and 3x1 plus 4x2 less than equal to 24. This is for the operation 2. These are the raw material considerations, very straightforward equations. But the question is that how to model X3 and what about the objective function? So X3, you see, we have, there are 2 parts. One is profitable, another is not profitable. So if you say that, okay, if X3 greater than equal to 5, if greater than equal to 5, then one kind of thing. If less than equal to 5, then another kind of thing. But then if you try to put those if-else kind of conditions, then what we are going to have is that we are going to have a non-linear kind of situation, because in a linear programming problem, moment you have if-then kind of considerations, we are going to have what is known as a non-linear kind of situation, and the linearity of the problem will be not be able to maintain. So this is the difficulty in this particular problem. So how do we model X3? All right, so this is what we have to think. So a good way is to define 4 different variables. So if you define 4 different variables, that is X1 is the product A produced, X2 is the product B produced, and X3 is the profitable part of byproduct C, and X4 is the destructive part of the byproduct C. That means that portion which not only is not profitable, and it has to be destroyed at a cost of 2 per unit. So one thing is very clear, that objective function can be very easily stated. So 4x1 plus 10x2 plus 3x3 minus 2x4, no issues there. But there are other difficulties. What are those difficulties? We already have those two constraints. Those are the raw material constraints. Now we have two more additional constraints to begin with. That is 2x2 equal to x3 plus x4. Because profitable part and destructive part together should be double the amount of the x2. So this is very straightforward equation. But x3 should be less than equal to 5. But look here, there is a nonlinear constraint also, and this constraint is most crucial because that makes the problem again nonlinear. So what is that constraint? That constraint is that, you see, suppose x2 equal to 5. All right. So if x2 equal to 5, then 2x2 equal to 10. Now x3 should be less than equal to 5 and x4 should be the rest of it. Now question is that x3 cannot be more than 5. But we are nowhere we are saying that x3 is let us say, suppose, is it possible that x3 equal to 3 and x4 equal to 7? This is another problem. And another problem is that suppose x2 equal to only 2. So if x2 equal to 2, then 2x2 equal to 4. If 2x2 equal to 4, then we are assuming that x3 should be entire 4, x4 should be 0. But suppose x3 then become 1 and x4 become 3. So basically, what we have to ensure that x4 should be 0 if 2x2 is less than equal to 5. All right. So as long as x3 is less than equal to 5, because x4 should be 0. So you see, when x4 equal in the initial portion, that is up to x3 less than equal to 5, x4 should be 0. Now the question is, how do we ensure that? Because this is a nonlinear constraint, right? So what exactly we should do? And how do we take care of this nonlinear constraint? So here is the complete formulation. That is, x1 is the product A produced, x2 product B, x3 profitable part of byproduct C, x4 is destructive part of byproduct C. So then maximize Z equal to 4x1 plus 10x2 plus 3x3 minus 2x4 subject to 2x1 plus 3x2 less than equal to 16. 3x1 plus 4x2 less than equal to 24. These are the raw material constraints in two different operations. 2x2 equal to x3 plus x4, x3 less than equal to 5, and x4 equal to 0 if 2x2 less than equal to 5. Now question is how to make use of this nonlinear constraint, and these are the non-negativity constraints. So this is the complete formulation. So formulation is done. Now we want to solve this problem. Now, if we want to solve it by the simplex algorithm, you know very well that we cannot make this constraint, right? This constraint cannot be entered. So how do we proceed? As a first case, let us assume that suppose we don't have this constraint, right? Let us assume that this constraint is not there. Let us try to solve the problem. All right. So you see, we have dropped the nonlinear constraint while solving the LP. So let us say that we have dropped, then we'll go through this logic little later. Suppose we have dropped this constraint, then what happens? So this is the original problem because we have dropped that nonlinear constraint. So this is a equality constraint, so we need an artificial variable. So we have already discussed this time and again, that if you have a less than equal to constraint, then you have to add a slack variable, then we can make an equality constraint. So this is what we have done. for the first constraint. If you have here again a less than equal to constraint, so we add a slack variable and there is no problem. But here is an equality constraint. So equality constraint, until unless you add one artificial variable, you cannot get the canonical form. That means the basic variables will not form a unity matrix because a +1 is required. This +1 is not there, and after all, x2, x3, x4, they are the regular variables, and these regular variables may occur in all the different constraints. So canonical form cannot be maintained. In order to get the canonical form for equality type of constraints, we need to add an artificial variable. So we added the artificial variable and we got the 0. And here we add another slack variables. And then we put this constraint, and look here, because it's a maximization problem, a -m is attached to the artificial variable, right? So in the profit coefficient, right? So that's how we have to then we can formulate the simplex fast table. You see S1, S2, A1 and S3, they are the basic variables. The 16, 24, 0 and 5, they are the what you call the values, and thereafter, so there are some difficulties here about the Cj minus Zj values because we have not taken this -m part. So you see for x2 there is a 2 here, so minus of -2m, so this would be not 0, but this will be 10 plus 2m, and this also not 0, this will be 4. So we can recompute the Cj minus Zj values which are not correctly put here. So those Cj minus Zj values have to be properly calculated and we can put. So here, like this one will be -m, it will be 3 minus m, and this will be -2 minus m, this will be 4 plus m, only 4 because of 0 here, and this will be 10 plus 2m. All right, so those are the Cj minus Zj values. But the bigger question is that this simplex, if I put it in that manner, what about this constraint that we have dropped? What would happen? You see, what is going to happen is that if you look at the augmented problem, a very interesting thing can be seen. That let us say that we have some value of x4. If we have some value of x4 and some other value of x3, but 2x2 equal to x3 plus x4, then you can have, with all the other values equal, you can have another solution where, supposing x2 equal to 2, and therefore x3 equal to 2 and x4 equal to 2. So current solution, x1 has a value x2 equal to 2, x3 equal to 2 and x4 equal to 2. So so you see, if you evaluate this, then 2, 2, 2, it will come to 10 into 2, 20, 3 into 2, 6, so 26, 26 minus 2 into 2, 4, so 22. It is evaluating to 22. So this is one solution, but supposing the best possible thing that may result is x2 equal to 2, x3 equal to 4 and x4 equal to 0. So what is the value then? The value is 10 into 2, 20, 3 into 4, 12, 32 and x4 is 8. So you see, when you have x2 equal to 2, x3 equal to 2 and x4 equal to 2, total objective function value is 22. When you have x2 equal to 2, x3 equal to 4 and x4 equal to 0, total objective function value is 32. So, simplex always works in such a manner that it goes from one point to the other, which returns the best possible value. So therefore, it will always discard the x2 equal to 2, x3 equal to 2, and x4 equal to 2 kind of solution, and it will always go towards x2 equal to 2, x3 equal to 4, and x4 equal to 0 kind of solution, because of the objective function and because the way the simplex works. So let's go back to the original formulation once again. So really speaking, we can simply drop the nonlinear constraint while solving in LP, because LP will ensure x4 will not come into the basis till full quota of 5 of x3 is exhausted, because profit coefficient of x3 is 3 and x4 is -2, and it is a maximization problem. So we are taking advantage of the simplex procedure, and we can formulate the problem, although we formulate the problem in this manner, but we can simply drop this constraint while solving by simplex, because of the typical characteristics of the simplex method. Is it all right? So this is the really another example where we have seen that how, in spite of having a nonlinear constant and we cannot do anything about it, we can still solve the problem by simply dropping it, because the nature of the simplex method is such that it will not return as an optimal solution something which is not going to return a better objective function value. Good. So now let us see a graphical linear programming problem. So in this problem, there are certain constraints. A company produces two types of paints, A and B. The company has a total production capacity of 11 tons of paints per day, A and B taken together. So if A is x1, B is x2. So what does it mean? That x1 and plus x2 should be less than equal to 11. That is one constant. Straight away we can see. However, at a time, the production facility can be utilized only for one type of paint, and it can operate a maximum of 16 hours a day. So that means, the production facility is such that only 16 hours is the total working time. Production of paint A requires 2 hours per ton, while of paint B require 1 hour per ton. That means 2x1 plus x2 should be less than equal to 16. We are ignoring the setup time or changeover time. So basically this first statement gives us two different constraints. One is x1 plus x2 less than equal to 11 and 2x1 plus x2 less than equal to 16. So these are the two different constraints. Now both A and B require a basic raw material for its production. 90 units of basic raw material is available. While A requires 5 units of this raw material per ton, B requires 6 units. So what does it give? What kind of constraint? That only 90 units are available. So 5x1 plus 6x2 should be less than equal to 90. So that is another constraint. Now, apart from this, the production of the paints also produces a byproduct which does not contribute to profit. However, at least 12 units of this byproduct must be produced. So see, if we have x1 is the first one and x2 is the second one. So A produces 1 unit of byproduct per ton, B produces 2 units of the byproduct per ton. So x1 plus 2x2 should be less than at least 12 units must be produced. So not less than, greater than equal to 12. And this byproduct has no profit contribution. So but then it only gives a constant. So we need not take any anything in the profit function or the objective function as in the previous problem. So profit for paint A is 1200 rupees per ton, while that of paint B is 1000 rupees per ton. So basically objective function maximize Z equal to 1200 x1 plus 1000 x2. So we have to graphically solve the problem. So as we have already discussed, so these are the constraints. Once again, let us review. let X and Y be the production of paints A and B respectively in tons per day. Hence, we have the objective function maximize Z equal to 1200 X plus 1000 Y. So it's very straightforward because of profit maximization. The first constraint is X plus Y less than equal to 11. This is the production capacity in tons per day. The second one is 2X plus Y less than equal to 16. Production facility utilization in hours per day. The third one is 5x plus 6y less than equal to 90, basic raw material utilization in units per day. And the fourth one, that is the byproduct, x plus 2y greater than equal to 12, requirement of byproduct production in units per day, and the non-negativity constraint x1 greater than equal to 0 and y greater than equal to 0. So what we have to do, we have to solve this problem in a graphical manner. So what we do, we take the two different axes, x1 and x2, and then try to plot the equality constraints, not the inequality constraints. So equality constant we plot, these will be straight line. One straight line x plus y equal to 11. Another straight line 2x plus y equal to 16, 5x plus 6y equal to 90, and x plus 2y equal to 12. Then we have to see that whether the origin is satisfied by this constraint. So for example, x plus y is less than equal to 11. So this constraint satisfies the origin. That means 0, 0 is less than equal to 11. So therefore, the inequality would represent the area between the origin and the straight line that we have drawn. That area will be your part of the solution space. In fact, out of all the different solution space domain found out from these four, the common area would be the actual solution space. So here also 0, 0 is satisfied. Here also 0, 0 is satisfied, but here 0, 0 is not satisfied. That means for these greater than equal to constraint, the the solution space would be on the other side of the origin. All right, so that is what we find from this equation. So exactly those are plotted here. So this is the line x plus y equal to 11. So it is this side. Then your 5x plus 6y equal to 90, but this line is too far away, so it become a redundant constraint mostly. Now 2x plus y equal to 16, so this line is here, so this actually this portion, and finally x plus y greater than equal to 12, that is this line that is on the other side. All right, so that would give this as the solution space. All right, so you can see that this is our solution space, and in this case there are certain points. So these are the 1, 2, 3, 4 different points are available, and we see that the maximum value, because we can evaluate here first of all 0.6. If you evaluate 0.6, we get 1200x plus 1000y. That means 0.6 would return 6000 only. All right, 0.11, how much it will return? 11,000. And this point also, we don't have this point value, but this point also would return less, and this point M would come as optimal, and the value at this point M is x1 equal to 5 and x1 y equal to 6. So Z would be 12,000. 1200 into 5 plus 1000 into 6. So what does it mean? The optimum solution is that we have to produce 5 units of the paint 1 and 6 units of paint 2. All right, so this is how we solve graphically such kind of problems. Now these blending problems are also very interesting. So in an oil refinery, the crude should contain 3 important components, A, B, and C. The refinery wishes its product to have at least 10% of A, 20% of B, and 12% of C. Now, it has got three different grades of crude oil, X, Y, and Z, with the following details. Grade X contain 15% A, 10% B, 9% C, and cost 2000 per barrel. Grade Y contain 18% of A, 25% of B, and 3% of C, and it's cost something. And same thing about grade Z, which has got various values. So first of all, it's a blending problem, because how do we blend X, Y, and Z in which proportion, right? So we can assume like 1 kg or a particular unit of total, and out of that unity, how much of these grade X, grade Y, and grade Z should actually be present. And total A, that is 15% of the amount of X, 18% of amount of Y, and 10% of the amount of Z actually should be the final product's 10%, right? So that should be maintained. So this is how we have to go. We have to see how the blending is done, and after the blending is done, we have to see that these A, B, C, etc. are maintained. And the objective function can be obtained from this cost part, which we have to minimize. All right, so this is how the let X, Y, Z be, I'm sorry, because these are the 2000 rupees barrel. So this is how the objective function, in this case, I think it won't be maximized, it will be minimized. So let X, Y, and Z be the amount of the three different grades of crude oil. So total amount of crude oil obtained is X plus Y plus Z barrels. And objective function would be minimize, not maximize, Z equal to 2000 X plus 2500 Y plus 1800 Z, because these are the different costs that are available. Now X, Y, and Z, so when you mix, the total amount is X plus Y plus Z. All right. So when it consideration of component A, it should be 0.15x plus 0.18y plus 0.10z. That should be greater than equal to 0.1 into x plus y plus z. So you see what happened? X is the first grade, second grade, y, and third grade is z. And 0.15, 0.18, and 0.1. Let's go back to the problem. So 15% of that grade X has got A. 18% is in the second, and 10% in the third. So what we have got is that 15% of X, 18% of Y, and 10% of Z, that should be, the greater than, because 10% of what? Of the total. What is the total? X plus Y plus Z. So this is the consideration of A. Similarly, the consideration of B and C should be 0.10x plus 0.25x plus 0.15z should be greater than equal to 0.20 of x plus y plus z, and such figures for the component C. Also, we shall have the non-negativity criteria, that is x greater than equal to 0, y greater than equal to 0, and z greater than equal to 0. So this is the complete formulation. Again, this is not maximization, it should be minimization, because these are costs. All right, and thereafter these are the different constraints, and we have the non-negativity constraints as well. Right, let's see another formulation problem before we close today. That is, at a post office, employees usually work for 5 consecutive days to provide proper customer service. The post office need the following number of employees each day. How many employees are required? Monday 10, Tuesday 8, Wednesday 7, Thursday 9, Friday 12, Saturday 15, and Sunday 6. Now the employees are paid on a daily basis. The payment for working on Saturday and Sunday are 25% more than on the other days. So if you work on Saturdays or Sundays, then you get more pay. How much more pay? 25% more pay. Now some employees are willing to do overtime and work for one more day, right uh, after their 5-day regular service. And overtime labor rate is 50% more than the regular labor rate. That means suppose someone works on Monday, if he gets one, if it is an overtime, then on Monday it will be 1.5. But on Saturdays and Sundays, because they are already getting 25% more, so it will be 1.25 into 1.5. Is it not? So because there will be double counting because they are already getting 25% more plus into not plus into 1.5, that will be the overtime rate. All right, now you see some people are joining on Monday. So they are working for 5 consecutive days. That means they are working on Monday, Tuesday, Wednesday, Thursday and Friday. Suppose out of the people who are joining on Monday, some are working for 5 days, some will be working for 6 days, right? So the Monday people, a fraction would be working till Saturday with overtime on Saturday. Others would be working 5 days only. All right, so this is for the people who join on Monday. People who join on Tuesday, they will be working for Tuesday, Wednesday, Thursday, Friday and Saturday. But some of them would work up to Sunday. With Sunday, they will be getting the overtime rate, that is 1.25 into 1.5. And both of them are working in Saturday, so they are getting 1.25 rate. Now people who are joining on Wednesday, some of them are working till Sunday and some portion, the overtime people, they are working up to Monday, and Monday they are getting overtime. Similarly, Thursday, right, the Thursday people, they are working Thursday, Friday, Saturday, Sunday and Monday, and some of them doing overtime on Tuesday. So you see, who are the people who are working on Monday? Monday, the regular people who are joining on Monday, they are working on Monday. People who are joining on Wednesday and doing overtime, they are working on Monday. People who are joining on Thursday, Friday, Saturday and Sunday, they are both regular and overtime people. They are working on Monday. All right, so this is how exactly we have to understand this particular problem so that we can, get into it. So let's say that the following number of people join on different days. Monday x1n normal, x10 overtime. Tuesday x2n normal, x20 overtime. Wednesday x3n and x3o, like this, and Sunday x7n and x7o. Right, so this is how we first define the different variables. And also the non-negativity constraints, all variables should be greater than equal to 0. So this is the first part, that is definition of these different variables. Then we see that number of people available on Monday will be normal from people joining on Thursday, Friday, Saturday, Sunday, Monday. So these are the people. Overtime for people joining on Wednesday. Is it not? So by this way, we can work out who are the total number of people available on Monday, total people available on Tuesday, total people available on Saturday, total people available on Sunday, and like that in the rest of the days. So essentially then the total people available on Monday will be that Wednesday overtime, Thursday, Friday, Saturday, Sunday and Monday normal time, and also overtime because these these days whoever is working, so we are assuming that that time is included in that. So normal salary is S. All right, so on Monday to Friday. So for Saturday and Sunday, it will be 1.25 S. Overtime salary will be Monday to Friday 1.5 S. Saturday to Sunday, it will be 1.25 into 1.5 S. So 1.875 S. So then from these figures, we can find out the objective function, right? Because let's say 1.25 into into x3o plus s into all these, s into all these, and these are the figures. Then all these numbers should be greater than equal to all these 10, 8, 7, 9, 12, 15 and 6. All right, so far so good. But one thing one should remember. You see, when we define that Monday, Tuesday, Wednesday to Sunday, that is X1N normal and X10 overtime. So these overtime people, they are also actually working. So, you know, when we talk about, there are two ways this can be done. One way is that these overtime people, you know, since they are also working, so that also can be added. That is one way of going. The other way of going is that we assume that when we talk about X1 normal, this normal includes the overtime part also. So you see what we have done, that when we say X1N, you know, these X1N includes X10. That means the total number of people of X1N, that whoever is joining on Monday, so out of them only a few are working overtime. So that also you see, like X10 part, if you look, so X10 part, they are available on Saturday. So you see total number of people actually joining. So the way it is modeled here is, it is not that X1N plus X10 number of people are joining on Monday. No, we are assuming that X1N people are joining on Monday in total. And out of that, only a few, supposing 20 people are joining, and 7 people are going to do overtime. So this means that Monday, Tuesday, Wednesday, Thursday, Friday, 20 people will work. And these out in these 20, these 7 people are also there. And those 7 people will work overtime on the 6th day. I hope it is clear now. So this is how the definition has been made here. Is it not? The suppose you don't want to make it like that, then in all other days we have to also add the corresponding O. That means total people on Monday would be X3O plus X4N plus X4O plus X5N plus X5O. So that is another way of looking at it. All right. So the problem can be seen from two different sides. One is that X1N, X2N, X3N, these are the total number of people that are joining on those days. Out of that, only a few who are also working along with the normal people for the regular 5 days, but they are going to work one additional day after the completion of the 5 days. Is it clear? So that is how this kind of problems can be actually tackled. So we have seen the assembly problem, one byproduct problem, how to formulate, and thereafter how to solve through simplex. The simplex fast table has been shown for you, and thereafter we have considered a graphical problem and showed how to solve it, and then two other formulation problems, which is one on blending and another on manpower requirement, we have also solved. Now, similar to this kind of manpower requirement problems, we can also have investment related problems that also can be solved in the similar manner. right? Anyhow, we'll not discuss this, and we stop here, and thank you very much for patiently hearing. All right, so thank you, and we stop here.